So what we're going to start out talking about today is differentials for functions of several variables. And so oftentimes differentials seem to be a lot more complicated or difficult than they actually are. The actual calculation of differentials is really not all that hard, right? It's essentially linear approximation, finding the tangent plane, taking the derivative in many ways, and we're using it again for estimation. Okay, what we're trying to do is we're trying to figure out the value for functions, or in the case of differentials, the rate of change, the relative rate of change for a function around a given point. So like basically we're trying to estimate the value of the derivative around a particular given point. And how we're going to use, what we're going to use is we're going to basically use a linear function for that. We're basically going to say, okay, so here's the derivative in this area, and here's the, for like x, here's the derivative for y in that area, okay? And then we're going to basically multiply it by the change in x and the change in y, add those two things together, and we're going to get the change in z, all right? And again, the whole purpose for this really is to allow us to estimate, in this case, the rate of change, okay, for a function, z, right, in a particular area, right? So again, it's an estimation. These things can actually be really kind of handy for us. They can be very efficient, which is actually really helpful as well. And they allow us to do some really good estimation. All right, so now let's take a look at this differential definition. And if you kind of remember the definition from differentials for single variable calculus, it'll look pretty much the same. So we got a function z, f of x, y, is a function of two variables with x naught, y naught in the domain of f. And we'll let delta x and delta y be chosen so that x naught plus delta x and y naught plus delta y is also in the domain of f. So we just need to make sure that we have our delta x and delta y so we don't go too far off, so that we stay in the domain of f. If f is differentiable at the point x naught, y naught, then the differentials dx and dy are defined as follows. So dx is going to be delta x, it's going to be the change in x, and dy is going to equal delta y. And these are going to be actual values, okay? So they're going to be numbers. When we do this kind of thing, they're going to be values. We're going to say, oh, I'm going to say within a boundary of 0.1 for delta x and 0.05 for delta y. So the total differential, dz, also called the total differential of z, equals f of xy at x naught, y naught, and it's defined as dz equals fx, x naught, y naught, dx, plus fy, x naught, y naught, dy. Okay, so what you're going to notice here, a couple of things. These are partials for f. All right, those are partials. We've seen those before now. And this thing here, that is not a partial. That's literally the change in x. Okay, so if you kind of think about that, that's going to be like an x1 minus x naught or x2 minus x1, except we're going to define it, right, as like a kind of like what we might call it a step size. All right, so we'll define that that differential as like a step size, and what that's going to give us is the change in z, which also again is not a partial. Okay, it is an estimate for the entire change of z if we're given the change in x, the part of the change in x around that region, and then the change in y around that region again. Okay, and so that basically gives us our definition. All right, so let's talk about a graphical interpretation of the differential. Let's see if I can do this. Let's say, for example, we're looking in 2 dimensions. So that we got y equals f of x. Okay, and we imagine we have a tangent line. If you remember, we've got this tangent line at the point. We'll call that x naught, y naught. There's your point. Okay, and what we want to do is we've got, here's our change in x. So our change in x, here's our x-axis. And say, for example, and this one's actually really close. Let's say we've got a change in x of a particular step size. All right, particular step size. All right, call that we'll call that delta x. And what we want to do is we want to say, okay, well, given the change of the step size, what's the estimate that we have for delta y in this case, or dx? And that estimate right there, that's going to be your dy. Okay, utilizing, by the way, using the tangent line. So as long as we're really close, and by the way, we can also go this direction as well for our delta x, because delta x is just a change in x. So given like a particular distance, all right, in the x direction, how much does y change? That's it. And what we're going to use, right, is we're using the tangent line in order to do that estimate. Okay? And that's kind of that idea. So now let's look at the tangent plane. And if you remember, we actually generated the tangent plane by, essentially taking the cross product of, right, call that our Fy, okay? And then we also took the and our Fx. So if you kind of imagine that we've got those two vectors that are going through this plane, or that kind of generate that plane. They're approximately that. It's kind of hard to show on the graph. Now, what we want to do now is we're going to say, okay, along this line, okay, if we kind of move that out and put that, like, created a vertical trace, we could create, right, our tangent plane has essentially this this line. Okay, if we pull that out, we're kind of pulling this piece out here. And here's our y value, and call this delta y. Okay, and this is Fy. Yes? So now what we're going to do is we're going to use Fy to approximate the change in z. Okay, so this is the part of the change in z, right? It's just part of the change in z, it's not the whole thing. And then we imagine, and this is kind of how I metaphorically imagine it. If it's not a perfect relationship, it's okay. Now what we're thinking is we've got this piece here, okay, which is the piece that goes with the x-axis, right? We've got the x-axis down here, and we've got, say for example, in this case, fx, which is going to do that approximation there, and say this is delta x, so that's a change in x, so we've got this piece that's a change in x, all right? And what we'll do here is we're like, okay, well, this is a change in z, right? A part change in z, it's not the whole thing. It's the part delta z, or maybe we'll call it delta z based on x, right? And that's just conceptually what's happening here. You've got these two parts. You've got delta z, we'll rewrite this as delta z based on y, and we have the delta z based on x. That's it, right? You put those two things together and you get dz, all right? Okay? And basically what we're doing here is we're doing the same thing that we were doing when we were doing the differential for a single variable, okay? But we're doing it in the two different directions of the plane, right? Our delta x and our delta y. So that's kind of the concept. Don't worry too much about it. Like, you kind of have to think about it a little bit. But basically what you're doing is you're saying, okay, I've got a function of several variables. Each one of those variables represents a piece of my derivative, okay? And so consequently, if I'm estimating my derivative, all right, then I've got to add up all of those pieces. All right, so let's find our differential. Let's look at an example. And say, for example, we have f of xy equals 3x squared minus 2xy plus y squared. We want to find the differential dz, and we're going to use it to approximate delta z at 2, negative 3. So really, I think it's just the vocabulary here that's actually very difficult. And I don't, it's just a matter of kind of like putting things together. It's studying like what it says here. So we've got dz. Remember, that's the change in z. And if you remember, that's going to be f of x, x naught, y naught, dx, plus fy at x naught, y naught, dy. And so what we'll need, for the moment being, right, we're going to have dx and dy, okay? Those are actually going to, in our differential, we're just going to keep them as dx and dy, right? And that's how we write out a differential. dz also remains the same. So we first want to start out with fx, x naught, and y naught. So we're going to find fx. So fx is going to equal 6x minus 2x. Excuse me, 6x minus 2y. And fy is going to equal negative 2x plus 2y. I'll write my differential now. dz is going to equal 6x minus 2y dx plus negative 2x plus 2y dy. Okay? And what we get here is actually something called an exact differential equation. Kind of cool idea. So what we need to do now is we're going to say, okay, so this is the actual differential. There's your differential, right? Pretty simple. If you're understanding, obviously, partial derivatives, right? If you don't understand what a partial derivative is, it's much more complicated. But dz equals 6x minus 2y dx plus negative 2x plus 2y dy, Okay? And what we're going to do now, okay, is we're going to need to figure out what our delta x and our delta y is. So let's just say, and I'm going to give it to you, and you will be given what your delta x is. Let's have delta x be 0.1. So in the x direction, we'll have 0.1. And in delta y equal to negative 0.05. Okay, there's your delta y. So what's going to happen now is, if you remember in our definition, we write that dx equals delta x. So that's going to equal 0.1. And dy is going to equal delta y. And that's going to equal negative 0.05. Okay? So what we need to do now in order to figure out what dz is, our approximation for delta z, is we'll first plug in, we've got to plug in x and y. So that's 2 and negative 3. So this is going to be equal to 6 times 2 minus 2 times negative 3 times 0.1 plus negative 2 times 2 minus, or plus 2 times negative 3. So we just plugged in the value 2, negative 3. And then our dy is negative 0.05. And there we are. And then all we got to do is just plug it into our calculator. So let's do that. And when I do all my math, what do I end up with? I end up with 2.3. So my dz, my approximation, is 2.3. Now for us to find actual delta z, and delta z is just the change in z, okay, what we're going to need to do is we're actually going to have to go out and we're going to find f of x plus delta x, comma y plus delta y, minus f of x naught, y naught. And actually these are x naughts and y naughts. So basically what we're going to do here is we're going to find out actually how much did z actually change. So remember that f of x naught plus f of xy, excuse me, is 3x squared minus 2xy plus y squared. Okay? And so what we'll do first is we'll figure out that we've got f of, and this is going to be 2 plus delta x, which was 0.1, 2 plus 0.1, comma, and then this is going to be negative 3 plus negative 0.05. And we'll subtract from that f of 2, negative 3. So this is going to be f of 2.1, comma, negative 3.05 minus f of 2, comma, negative 3. And when we actually plug those values into our function, what do we get? We get 2.3425. Okay? And so that actually is not too huge a difference, right? This is the actual difference in delta x. This is the estimate using dz. What we're going to call the difference between delta z and dz is the error. Okay? Anytime we have an actual, right? Anytime we have an actual value and we have an estimate, the difference between the actual and the estimate is what's called an error. And so, you know, and we've talked a lot about that, and you've talked a lot about that in previous calculus classes, but it bears repeating, okay? Anytime we do estimates, we have an error. And so in this case, 2.3425 minus 2.3, that means our error is 0.0425. And that's the actual error, okay? If you go in, we calculated delta z. We utilized our differential in order to calculate dz, okay? So our error is the difference in the two, and that ends up being 0.0425. Okay, so this completes the mini lecture on differentials. Differentials, again, are a way for us to go through and estimate the value for the derivative, or for a change in z, actually. It's really the change in z, not the derivative itself. The change in z, okay, utilizing the tangent plane this time instead of a tangent line. All right, hope that helped.